Yes, screen is visible, na? Hello?
Yes, sir.
Yes, sir.
Yeah. Okay. So today we will be discussing about this digital pulse amplitude modulation, that is PAM, okay, transmission through band limited baseband channels. Okay. So you are aware of what is PAM, pulse amplitude modulation? I'm asking you people only. Have you studied anywhere about PAM? I hope you are studied in principles of communication system.
Sir, we had it in PCS.
Yeah, PCS, no, as a last module.
We had it in PCS, but it was not.
No, okay. Just to brief the what PAM is, see, pulse amplitude modulation, right? Means the amplitude of the pulse varies. Okay, here I am using a carrier as a pulse that varies according to the information signal. That's all. That is known as pulse amplitude modulation. And even here I can have, if I use just 2 bits, means 0 and 1. 0 I can represent with one amplitude level, and 1 I can, in information bit 1 I can represent with another amplitude level. So if I go for M array, right, M array PAM, means the moment I say M array, say like in QPSK, right, what we do with the 2 bits, 4 combinations, right, 0, 0, 0, 1, 1, 0, and 1, 1. So there I used to have 4 phase shifts, right? They are of quadrature difference, that is 0 degree, 90 degree, 180 degree, and 270 degree. Or I said 45 degree, 135, 215. So similar to that, here the value of amplitude level will vary in case of PAM. So if I say 2-bit PAM, means 0, 0, 0, 1, 1, 0, and 1, 1, right? So I can represent these 4 bits, means 0, 0, 0, 1, 0, and 1, 1 with 2 different amplitude levels, right? So for 0, 0, I can say plus 3, and 1, 1, I can say minus 3. Similarly, 0, 1, plus 1, and 1, 0, minus 1, like that. So I hope you could visualize that. 4 different amplitude levels. Okay, that is with a 2-bit. If it is 3-bit, then 8 possible combinations, right? That is from all 3 zeros to all 3 ones. That is 000 to 111. So I can decide the number of amplitude levels, right? So with 4 bits, I said 4 amplitude levels. With 3 bits, I can have 8 different amplitude levels. So that is what the PAM is. Okay. So could you visualize what it is? Here amplitude, we are conveying the information bit with the amplitude. That's all, amplitude of the pulse. Okay. So is it clear? Hello? People are not talking. Is it clear?
Yes, sir. Yes, sir. Clear, sir.
Clear. See, once you understand any MRA modulation, okay, whether we vary phase or frequency or amplitude. So here we are varying the phase of the signal. Okay. Fine. So this is the block diagram of the digital PAM system. Okay. So the input data will be applied to the transmitting filter. So this transmitting filter have an impulse response of GT of T. Okay, in frequency domain we say it is GT of F. Okay, so output of this transmitting filter is denoted as V of T. That will be applied to the channel, and this channel having a frequency response, right, as C of F. Okay, so this we have discussed yesterday, right? A linear filter channel. Then noise will be added in the channel. So R of T is the what received signal at the receiver. That is what output of this channel, means a transmitting filter and channel together I can represent as H of T. So and noise will be added to that, right? So that will be the R of t, the received signal. That is applied to the receiving filter, and this receiving filter will have a impulse response of GR of t. Okay, and in frequency domain, I represent that as GR of f. So output of this receiving filter, I am denoting it as Y of t. Okay, so that will be sampled. Okay, so this is what the means it will be sampled at right interval, right time, then only I will be able to achieve the maximum signal to noise ratio, what I discussed yesterday in the matched filter. So I will be sampling the output of the receiving filter. So this sampler output is given to the detector. Okay, so the sampler needs the timing signal. Okay, so that will be extracted from this received signal only. So that acts as a clock to this sampler. Okay, so that will specify the appropriate time instant to sample the output of the receiving filter. Okay, so I said in case of matched filter at t equal to t, right? Means if I take a square pulse, right, of duration 0 to t, if I sample that signal at t equal to t, then I will be able to get the maximum SNR, that is the output of the matched filter. So that will be decided by this. Okay, so this is in brief about the block diagram of the digital pulse amplitude modulation system. So let me take in depth about each. Means how do we represent input data sequence, output of the transmitting filter, what is the output of channel filter, then other things. Okay, so here I'm saying the input binary data sequence, right, will be applied to the transmitting filter. At what rate? Means it is having a bit rate of RB bits per second. Okay, from the source, that is subdivided into k bit. So here this k may be 2 bits or 3 bits or 4 bits, that depends, right? So k bit symbols, and each symbol is mapped into the corresponding amplitude level. Okay, that will be modulated by the this transmitting filter. So it is written here very in general. Okay, I gave an example when the value of this k is 2, how many amplitude levels I will get, and when k equal to 3, how many amplitude levels I get. Right? I said when k is equal to 2 means 2 bits is one symbol. So I can have 4 different amplitude levels. I said for 0, 0 plus 3 volts I can take. Then for 0, 1 say plus 1 volts. Then for 1, 0 minus 1 volt. And for 1, 1 say minus 3 volts. Similarly for 3 bits also you can decide with 3 bits, 3 zeros to 3 ones. Right? So what I said is the input binary data sequence with a bit rate of RB bits per second from the source is subdivided into k bit symbols, and each symbol is mapped into the corresponding amplitude level, which will be modulated by the output of the transmitting filter. So sorry, I can write the baseband signal at the output of the transmitting filter, that is at the output, that is the input, that is at the input of the channel. See, in the previous case, this is the block diagram, right? So output of this transmitting filter I denoted as V of t, and this is input to the channel, right? So that is what I am saying here. The baseband signal at the output of the transmitting filter or at the input of the channel will be given like this. And V of t is equal to summation from n is equal to minus infinity a n gt of t minus nt. Let's see. Here this t is what? K by RB. So k is number of bits, right? K bits per symbol, and RB is a bit rate, right? That is the symbol interval, what I can say. Right? Because bit rate RB is 1 by TB. So symbol interval will be 1 by RB into K. K is number of bits. Right? If I have then so I said RB is a bit rate, and this A suffix N is the what? Is a sequence of amplitude levels. Right? I told about the amplitude levels already. Right? Corresponding to the sequence of K bit blocks of information bits. Okay. So this amplitude level, and GT of T is what? GT of T is the impulse response of the transmitting filter. Right. So it will be multiplied and summation we will get. you can visualize from minus infinity to plus infinity. So the value of n varies from minus infinity to plus infinity. So series of pulses will be there. That will be multiplied with the impulse response of the transmitting filter. So that is the output of the transmitting filter, V of t. Okay. Then, okay, this is the output of the transmitting filter, right? So next is I'm talking about the received signal. So I said received signal at the demodulator. Means that is what, that is the output of the channel, right? Is given as R of t. So which is equal to what? Summation from n equal to minus infinity an h of t minus nt plus noise, right? The noise is also added in the channel, I said. So this h of t here I have taken. So that is what impulse response of the cascade of the transmitting filter and the channel. Okay. So h of t is the what impulse response of both the blocks, that is transmitting filter and as well as the channel. There is a written h of t is equal to c of t converted with gt of t. So this c of t is the impulse response of the channel, and this gt of t is the impulse response of the transmitting filter. Right? The convolution of those two will give you the value of h of t. Right? And as I said, n of t is the additive Gaussian noise. So this is what the received signal R of t. Okay, this received signal is passed through the linear receiving filter with an impulse response of what? Gr of t. Right? And in frequency domain, we write that as Gr of f. Right? So the Gr of t means the impulse response of the receiving filter is matched to what? The impulse response of the cascade connection of transmitting filter and the channel. That is h of t. Right? Then only it is possible to achieve the maximum output SLR. Right? At the proper sampling instant. So I can represent the output of the receiving filter as y of t. So that y of t will be written as like this: summation n is equal to minus infinity an x of t minus nt plus noise. This is w of t. Okay. So is it clear about these three equations? What I wrote? What v of t? V of t is the output of the transmitting filter, right? So this is a data sequence an that will be represented by that amplitude level depending upon the bits, and gt of t minus nt is the what? Is the impulse response of the transmitting filter, right? And this R of t is a what? Received signal at the receiver, right? What I can say, it is output of the channel filter. So again, see, h of t is the what? Impulse response of the cascade of transmitting filter and the channel. So that amplitude level bit sequence is multiplied by the impulse response of cascade of the transmitting filter and the channel, right? Plus n of t is the noise, isn't it? So the output of the receiving filter y of t will be written like this. So again, the amplitude level and output of the filter is x of t minus nt, right? Plus noise. As I said, the receiving filter having an impulse response of what? Gr of t, right? And as I said, h of t is equal to what? Yes, c of t converted with gt of t. C of t is the what? Impulse response of the channel filter, and gt of t is the impulse response of the transmitting filter. So this h of t has to be matched to the gr of t. What is gr of t? Gr of t is the impulse response of the receiving filter. So if this gr of t means impulse response of the receiving filter matches to the impulse response of the h of t, then only it is possible to get a maximum output SNR, right? So output of the receiving filter, I will be denoting it as y of t. I will be writing y of t as like this: series of pulses with convolution of that impulse response of that particular filter plus noise. Okay. Okay. So as I said, x of t, right, is equal to h of t converted with gr of t. So what is h of t? That is c of t converted with gt of t, right? And that is converted with gr of t. Right? gt of t, I said it is the impulse response of the transmitting filter, C of t is the impulse response of the channel filter. GR of t is the impulse response of the receiving filter. Right? So that is X of t. Then W of t, I said it is a white additive white Gaussian noise. Right? So that is also converted with the impulse response of the GR of t. See, this N of t is additive white Gaussian noise. That is converted with GR of t. So that I represent as W of t. Okay, so this is the additive noise at the output of the receiving filter, W of t. I hope I'm able to make the difference. See here, N of t is the additive white Gaussian noise in the equation 10, and W of t is the output of the receiving filter along with the noise. So that will be what? That is a convolution of additive white Gaussian noise and the impulse response of the receiving filter. Right. So our aim is to recover the information symbols AN. Right. So to recover the information symbols AN, the output of the receiving filter is sampled. Right. I said periodically with the interval of t seconds. Right. So I can write output of the sampler. Okay, the block diagram output of the receiving filter is given to the sampler, right? And the clock is extracted from the received filter, received signal, and it will be sampled at t equal to capital T. Right. So this is the output of the sampler, what I can say. The y of m into t, which is equal to summation from n equal to minus m to infinity a n x of mt minus nt plus w of mt. And I can write with single suffix, that is y suffix m is equal to, so that is summation n is equal to minus infinity a n x m minus n plus w m. So I am substituting here the value of n equal to 0. So when n is 0, I get this is what n is 0. I think I should write it should be xm and a naught, right? Right, when n is 0. Then plus other values when n is not equal to m. Okay, this is the case where when n is equal to m. Okay, the first term is what? When n is equal to m. So when n is equal to m, I get x naught. Right, I can write this as am. So x naught am plus other symbols. That is when n is not equal to m. I get an x m minus n plus wn. Right. So here, see, xm is equal to x of m into t, and wm is w of m into t, where the value of m can vary from 0 to plus or minus 2, and so on up to plus or minus infinity. Right. So in this, the desired signal is this x naught am, and this x naught is the gain. Okay, am actually the desired symbol. Like in the transmitter side, I said the information symbol denoted an, right? In the receiver side, I am denoting that as am. That is multiplied with some gain, that is x naught. And the second term, what I say, this is due to intersymbol interference, means addition with the present and previous symbol, right? This is the successive symbols addition, present and previous. Right? And this is the additive with Gaussian noise. Okay. I hope this equation is clear. Three terms I get at the output of the detector. This is the output of the sampler. So I said ym is equal to this equation. In this, when I make m equal to n, so I get what x naught am plus rest of the term I'm writing, and next noise. But I said this is the what? First term is the desired symbol or desired signal, what I can say. And here x naught, I said it is the gain, and am is the signal. Okay, information symbol. And the second term, I'm saying that is due to intersymbol interference, and this is the additive white Gaussian noise. Yes, if you have any doubts, you can ask about this, writing these equations. Just this summation term I have written instead of integral convolution. That is written summation, since it is a discrete. Yes, sir. Is it clear, or do you have any doubts regarding writing these equations? V of t, starting from V of t to R of t, then Y of t, then Ym. Hello? Nobody is there. Lost. 37 people are there. Yes, please respond. No? Anyone?
Yes, sir. Yes.
Sausanya. Is it clear now what the equations I wrote?
Yes, sir.
These equations are clear. I told about this.
Yes,
I was talking about digital PAM transmission, right? Transmitting filter, channel, receiving filter, sampler, and detector. I said, what is the output of the transmitting filter? Okay. Then I told about what is the received signal at the receiving filter. Then output of the receiving filter, we'll be denoting it as y of t is like this. Then I said it will be sampled at t equal to t. So this is the output of the sampler. Then this ym, right, which is equal to, I write like this, and I said in this the first term is the desired symbol, and second term is due to ISI, and third term is the noise, read-weight Gaussian noise. I said here x naught, what I'm getting is the gain. Okay, AM is the symbol, desired signal. Okay, so that's what I told here. The first term x naught AM and the RHS of that equation is the desired symbol scaled by the gain parameter x naught. Okay. Fine. So I'm saying here what is the value of x naught. So when the receiving filter is matched to the received signal h of t, the scaling factor will be given by this equation, integral from minus infinity h square of t into dt. So if I substitute in frequency domain, it will be h of f squared df. I know what is h of f, that is the multiplication of gt of f into c of f, right? I'm taking square. So its value will be equal to EH, that is energy of the output of the impulse response of those two cascaded filters. Okay, and I said the second term on the RHS of that equation 13 represents the effect of other symbols at the sampling instant, say t equal to mt. So I said that we call it as a ISI, that is inter-symbol interference. Okay, so in general, what I can say is inter-symbol interference causes the degradation in the performance of the digital communication system, right? I said already about third term, that is the additive noise, right? It has zero mean, and the variance will be this much, and not ES by 2. Okay? So, to conclude this topic, what I can say is, by appropriate design of transmitting filter and the receiving filters, right? So it is possible to satisfy the condition, means xn equal to 0 for all n is not equal to 0. So that the inter-symbol interference term will be vanishing, means the second summation term should vanish. So that is possible. Xn should be equal to 0 when n is not equal to 0. Okay. Then the second term will be vanishing. Okay. So here what we have considered in this discussion is the only term which causes errors in the received digital sequence is the additive noise. Means if I design a proper transmitting and receiving filter, if it satisfies this condition xn equal to 0 for all n is not equal to 0, then if that term vanishes, the second term, then the error in the received symbol is due to only this additive noise only. I think, yeah, in this equation 13, if xn is equal to 0, when n is not equal to 0, then this term will vanish. If I make xn equal to 0, right? Then the output of the sampler will be what? X naught AM plus this WM. So during that time, the error is only due to this additive noise I wanted to say. Okay. If this thing is clear, then I will go to the next topic. You all people should say is, are you happy with all these things? Have you noted this block diagram? Hello? Alert.
Yes, sir. Yes, sir.
Yeah, Vishnu is active, but Chandan also sometimes says yes, sir. Saujanya talks. Others I'm not hearing their sound. Let me see overall. They are there. Let me alert some people. Abhilash, Aishwarya,
Yes, sir.
Akshata is not talking. Could you understand ma that block diagram?
Yes, sir.
Block diagram of digital PAM system, and what is the output of the sampler, and then how do I say how I can minimize the intersymbol interference? What should be the condition and all? You could understand that.
Yes, sir.
I said if xn is equal to 0, for all n is not equal to 0, then the second term will vanish. Only output of the sampler will be equal to what? X naught AM plus WM, where WM is the additive white noise, right? So error will be only due to that noise, not because of the successive symbols. Okay. So is that topic is clear? Then I will go to the next topic. Okay, next we will be talking about signal design for band limited channels. Okay. So now let us consider the problem of designing a band limited transmitting filter, okay, under the condition that there is no channel distortion. Okay. So we are considering the what problem of designing a band limited transmitting filter under what condition? There is no channel distortion, right? So this h of f is the what? Is the frequency response of the output of the frequency response of transmitting filter and the linear channel, that is C of f into GT of f. So in time domain I have written, in frequency domain I have written here. Earlier I told about told in the time domain. So means I was telling about h of t, which is equal to convolution of C of t with the GT of t, right? Okay. In frequency domain, obviously it is multiplication of their Fourier transform. Right? So for distortion-free transmission, the frequency response characteristics of this channel has, means the frequency response characteristics of the channel has a constant magnitude and a linear phase over the bandwidth of the transmitted signal. Okay, what I said, the value of h of f. Okay, if we say the channel is distortion free, right? The frequency response characteristics of the channel has what? Constant magnitude and a linear phase over the bandwidth of the transmitted signal. So I am writing C of f as like this: C naught into e power minus j 2 pi f t naught over the frequency, when f is less than or equal to w, and its value will be 0 when f is greater than w, and where w is the available channel bandwidth, and t naught is the arbitrary delay, okay, time delay, and I can set that to 0. Okay, if I set that arbitrary finite delay to 0, then the value of C naught will become 1. Okay, for my convenience, I am assuming C naught is actually gain factor, which I will be setting to 1. So you can visualize the diagram with a rectangular pulse which exists from minus W to W, okay, with a magnitude of 1. That's all. That is the value of C of F. That is the frequency response of the channel. Okay. Since I say the channel is distortion free, so H of F will be equal to what? GT of F when F is less than or equal to W, and it is 0 when F is greater than W. Okay. Why it is H of F equal to GT of F? Because the value of C of F will become 1. Right. I said the C naught is constant gain factor, for which I said I will be treating it as 1. Right. So C of F value will be equal to 1 when F is less than or equal to W. That is why I write H of F as GT of F only. Okay. The value of C of F is 1 over this frequency range. So the master filter output as a frequency response that we say conjugate, okay, which is equal to H conjugate of F is equal to G conjugate of F. So here it is GR of F or GT of F, transmitter filter. And its output at the periodic sampling time T equal to MT can be written as, so already I told this equation, right? Y of MT is equal to X of 0 into AM plus when N is not equal to M, I get this plus this is due to relative noise. Or in simple notation, I can write Ym is equal to X naught AM plus N is not equal to M, I get AN X M minus N plus WM. Right. So here X of T is what GT of T converted to GR of T. So X of T is the what output of the receiving filter, and W of T is the what output response of the matched filter to the as the input. Okay. So the second term in this equation, right, represents what? This is due to ISI, that is intersymbol interference. Okay. So I will be able to see what is the amount of intersymbol interference and what is the amount of noise added to the desired signal in an oscilloscope. Okay. So that we call as I pattern. Here I am saying the amount of ISI and the noise in the received signal can be viewed on the vertical input of an oscilloscope. Okay. So the received signal is displayed on the vertical input with the horizontal sweep rate set at 1 by T, where 1 by T is the what bit rate of the input signal, right? Means for horizontal sweep, I need to set at that 1 by T. For vertical, means in oscilloscope, we have two channels. One is X channel and Y channel, right? So if I apply input to the X channel, and if I apply a sweep rate at what 1 by T to the horizontal plate, means Y is this one, I will be getting a display on the oscilloscope. That display is known as the I pattern. Why I call that as I pattern is it resembles the human eye. Okay, that is why it is called I pattern. And what it will convey that I pattern, in that I pattern, I will be able to see the effect of intersymbol interference and as well as noise, which is added to the desired symbol. Okay. That is what the I pattern is. Just I am showing you the diagrams of that. See, this is when the input sequence is binary, means only two values, binary, that is 0 and 1. 0 represented with one symbol, one amplitude level, and 1 is represented with another amplitude level. So this is how I get on the oscilloscope. I hope everybody is able to see this diagram.
Yes, sir.
So this is when I make input sequence as binary, and this is for quaternary, means 2-bit is one symbol, okay, with 4 amplitude different levels. So I get 1, 2, 3, 4. So this almost look like I only, no? That is why it is called I pattern. Okay, it resembles the human eye shape. That is why it is called I pattern. So I will be see here when so just I will give information about this I pattern, what it is, right? Just have a look about this diagram. So what are all the things are written here? See this time, that is from this. So this is the eye opening, right? This what I shown. I'm moving the cursor. This is eye opening. Okay, eye this one. See, from this point to this point, we call as sensitivity to timing error. Okay, and at the center, no, this is the optimum sampling time. What we say, okay, center point. This point is the optimum sampling time. Means at the receiver, if the sampler samples at this time, then we'll be able to get the proper signal. Okay, so this is optimum sampling time, and here slope is also there, right? This slope, I will come back to that. And this one is the peak distortion between these two lines, and I call from here to here as the noise margin. Okay, and this term is the distortion of zero crossings. I will give more detailed information about this, what each term is, and all in the coming slides. Okay, just have a look about this, and these are all the terms which we obtained from the I pattern, and it is an important topic for examination point of view also. So they will ask, write a brief note on I pattern like that. So you have to take some example and you have to write this diagram and you have to explain all these terms. I will throw some more light on this with proper explanation. I will come back to this. Okay? Just I am showing different diagrams which where these are simulated outputs. Okay, so this is one. Okay, I hope this shape is I shape. The MATLAB output, you can check in MATLAB also. This diagram. This is just I what I consider binary. Right? Binary 1 represent with one this one, right? And then binary 0 with another one. This is for quaternary what I say. Okay. So let me take now some more other slides where I can throw you more light on this pattern. Okay.